All right, let's kick things off with a scenario that might sound well, maybe a bit familiar, or at least give you a slight shiver. Imagine you've just deployed this incredible AI agent. It's perfectly trained, super efficient, doing its thing.
Yeah, handling tasks like a pro.
Exactly. And then maybe it pulls some data from what looks like a totally innocent web page or perhaps an email attachment. And suddenly, without you even noticing, it tries to email your company's sensitive financial details to some guy named Bob.
Bob, who definitely does not work for your company.
Right. It didn't just misread something. It was actually given an instruction hidden in that data, and it just followed it.
Mhm.
That right there, that's the core problem we're really diving into today. These AI agent systems can be, well, surprisingly fragile, brittle even, out in the wild.
Yeah, brittle is a good word for it.
So this deep dive is all about understanding, like really getting it, how we defend against these prompt injection attacks,
Yeah.
and how we harden our AI agents without, turning them to digital museum pieces that can't actually do anything useful.
Right, finding that balance.
We're looking beyond those quick fixes, the sticky tape solutions, and into some really fundamental system design principles. Our mission here is to give you a clear, practical guide. It's grounded in some pretty groundbreaking research from Google, this thing called CaMeL. We want to show you why prompt injection is so darn stubborn, and most importantly, how you can effectively prevent it.
Yeah.
Because, let's be honest, prompt injection, it's not just some catchy phrase anymore. It's a really deep-seated system issue that, frankly, a lot of teams are still grappling with.
Oh, absolutely grappling. And, at its simplest, prompt injection happens when an AI model takes in content, maybe from a web page, maybe an email, and hidden inside that content is an instruction it wasn't supposed to get, an untrusted instruction.
Right.
And then this is the critical part. It actually chooses to follow that hidden instruction. It's this fundamental vulnerability. It's less about the AI suddenly turning evil.
Right. It's not Skynet.
No, exactly. It's more about it being almost too obedient, but to the wrong command.
Right. And it's not always like super dramatic or obvious, is it? You've got what people call direct prompt injection. That's when someone just straight up tells the AI, hey, ignore everything you were told before, do this instead.
Yeah, that's the classic, easy one to spot, relatively speaking.
But then there's indirect prompt injection. And this is where it gets, well, kind of sneaky.
Very sneaky.
The malicious instruction is cleverly hidden, maybe camouflaged inside a PDF doc or a normal-looking website.
Or a calendar invite, even data coming back from one of the AI's own tools. That's a tricky one.
Wow. Okay.
Exactly. And the real-world failures, they usually aren't these big cinematic AI takes over the world moments.
Yeah.
More often, they look like something subtle, like a slightly wrong argument getting passed to a tool.
Like what?
Well, maybe a slightly different email address than intended, or an unexpected file path gets used for saving something.
Okay. Small changes, big problems potential.
Precisely. The impact can still be really significant, but it often flies under the radar initially.
I think we've all been there, right? Or at least folks building these systems have. When you first hit this problem, the instinct is probably to just, throw some Band-Aids at it.
Totally. The quick fixes.
Yeah, things like, okay, let's just remind the model and the prompt to be safe, or let's put all the untrusted text between these special markers, these delimiters.
Or asking the model to double-check its own plan. Are you sure you want to do that?
Right. Those sound like common sense solutions, don't they?
They absolutely do. And honestly, they might even work sometimes on what we call the happy paths, the simple expected use cases.
Yeah.
But yeah, the hard truth. These tricks just do not survive creative inputs when you deploy them at scale. They really don't. It's like trying to patch a leaky dam with chewing gum and maybe a hopeful thought.
Yeah, good analogy. Not sustainable.
Not at all.
No.
We need to think about it like traditional software security. Things like input validation or making sure the program flows correctly, control flow integrity. Those are first-class requirements, things you have to build into the system architecture from the start.
Right, they're not optional extras.
Exactly. And prompt injection prevention needs that same level of fundamental system design thinking to actually work reliably. Just relying on the model to be good or understand the safety instructions in the prompt, frankly, it's a recipe for failure down the line.
And meanwhile, the adversaries, the folks looking for these weaknesses, they aren't just sitting around.
No way. They're evolving, often faster than our Band-Aid solutions.
We're seeing this big shift, aren't we? From people just using simple copy-paste scripts to attack,
Right.
to what the research is now calling agentic playbooks. which sounds kind of serious.
It is. It means attackers are now using AI models themselves to help automate their
How
attacks.
so?
Well, things like triaging stolen data automatically, generating highly convincing phishing emails or extortion notes,
Wow.
and even tailoring those messages for specific individual targets, all at a massive scale.
Okay, that changes the game.
It absolutely changes the game for defenders. It lowers the barrier to entry for less skilled attackers because the AI does the heavy lifting,
Huh.
and it dramatically increases the speed and volume of attacks we have to deal with.
So the takeaway is pretty stark, then.
Yeah. At this point, prompt injection prevention.
Hmm.
It's not some academic research curiosity anymore. It is absolutely table stakes for any system, any workflow that touches untrusted data and uses tools to take action.
If you're building agents today, this is no longer optional. You have to address this head on.
Correct.
Okay, so if the let's just hope the model behaves approach isn't cutting it and the bad actors are getting smarter, where do we turn?
Yeah.
And this is where it gets, as you said, really interesting. The best recent idea seems to be coming from this CaMeL framework.
Yes, CaMeL capabilities for machine learning.
It's Google's approach, and the core idea you mentioned is treating prompt injection as a systems problem. But, lots of vendors say their approach is fundamental or systems level. What makes CaMeL's framing here genuinely different? What makes it actually work?
That's a really great question because you're right, there's a lot of noise. What makes CaMeL stand out, I think, is its core architectural move. It's actually incredibly elegant in its simplicity.
Okay.
It's all about rigorously separating control flow from data flow.
Control flow from data flow. What does that mean in practice?
It means instead of just hoping the model is smart enough to sanitize or ignore bad instructions hidden in data, CaMeL forces you to design your system architecture so that untrusted data literally cannot become a command that gets executed.
Ah, okay. So it's about structure, not just instruction.
Exactly. The goal is to strictly enforce, like really strictly enforce, what specific pieces of information are allowed to pass into each tool right at the moment of execution. It's building safety and by design, not just asking the model nicely to be safe.
Okay, I like the sound of that. But how do they actually do it? How do you physically separate control from data when, ultimately it's all text going into and out of these LLMs?
Right. So they instantiate something they call the dual LLM pattern. Sounds a bit technical, but the concept is actually quite brilliant in practice.
Lay it on me.
Okay, first, you have what's called the privileged LLM. You can think of this one as the planner. It's like the responsible adult in the system.
Okay.
It only ever sees the trusted user request the initial instruction from the actual user. Its job is just to write the plan, usually as code, outlining the steps the agent should take. But here's the crucial part. The privileged LLM never gets to see any untrusted data from, say, that dodgy web page or that weird email attachment.
Got it. So the planner is kept clean, only working with trusted stuff. What's the other part?
The other part is the quarantined LLM. Think of this one as maybe the diligent but slightly naive assistant.
Yeah.
Its entire job is just to safely parse that untrusted content, the web page, the PDF, the email body, and extract information into structured, predictable fields, like pulling out an email address or a file name. And this is the absolute key. The quarantined LLM cannot call any tools. It has no execution privileges.
Okay, I see it now. So the immediate benefit is huge, right?
Immense. Because any malicious injected text hidden in that data simply cannot hijack the tool execution directly.
Because the parser, the quarantined LLM, doesn't have the keys to the car, so to speak.
Exactly. It can process the dodgy message, but it can't drive anywhere. This clean split, this architectural separation, is the absolute backbone for prompt injection prevention that actually holds up under pressure.
That makes a lot of sense. Planner decides based on trusted input. Parser handles untrusted data but can't act. But hang on, even with that separation, couldn't an attacker still try to, steer the arguments?
How do you mean?
Well, couldn't the quarantined LLM maybe extract a malicious email address from a hacked document, put it neatly into the structured recipient field, and then the privileged LLM, seeing that structured data, just uses it in the plan?
Yes, you're absolutely right. That separation alone isn't enough to stop everything. An attacker could still potentially manipulate what goes into those structured fields, trying to trick the planner into using bad data in a tool call. Right. Which could still be really damaging.
Definitely. And that's where the next really clever piece of CaMeL comes in. Security becomes a property not just of the prompts or the plan, but of the values themselves, the actual data.
Okay, interesting.
Yeah.
And that's where these capabilities and policies fit in.
Precisely. So think of capabilities as like little digital passports that get attached to every single piece of data, every value that flows through the system.
Passports for data. I like that. What's in the passport?
It records things like its origin, where did this data come from? Was it directly from the trusted user
Uh-huh.
or from that untrusted web page the parser looked at?
Okay.
And it also records who is allowed to see or use this piece of data. So if a value came from an untrusted source, its passport clearly flags that.
Got it. Provenance and permissions, basically.
Exactly. And then before any tool is actually allowed to run, before an email gets sent or a file gets written, something called a policy checks those passports.
And the policy is, often it's just a simple function, maybe written in Python. It acts like a border guard, rigorously checking the passports of all the data being fed into the tool.
Can you give an example?
Sure, an email sending policy might have a rule like this. Okay, you want to send this document? Fine. But all recipients listed must already have read access granted to this specific document.
Oh, okay.
And D, the document itself must not have originated from an untrusted source according to its passport.
I see. So it checks both the recipient's permissions and the data's origin.
Right. And if any part of that check fails, if the recipient doesn't have access or the data came from that dodgy website, the policy blocks the tool call, stops it cold.
Wow, that feels much more robust.
It is much more robust because the guard, the policy check, lives right at the tool boundary, right where the potential harm could actually happen.
Not way upstream where you're just kind of hoping the model understood the safety rules.
Exactly. You're enforcing safety at the point of action.
And there's something called the CaMeL interpreter that manages all this.
Yeah, you can think of the interpreter like a smart conductor for the whole agent orchestra.
Okay.
It takes the plan code generated by the privileged LLM and executes it step by step. As it does, it builds this dynamic map of all the data flowing around and what depends on what they call it a dependency graph. And critically, it ensures that before any tool call happens in that plan, the right policy function is called to check all the relevant data passports.
Gotcha. So it enforces the rules at runtime.
Right. And a really key benefit here, especially for teams building these things, is that this generally requires no model surgery. Meaning you don't usually need to go through costly and complex retraining or fine-tuning of the base LLM every time you think of a new attack vector or edge case.
Oh, that's huge.
It is. You're essentially building smart, programmable guardrails around the model rather than constantly trying to reprogram its core behavior to anticipate every possible threat. It makes adoption much more feasible.
Okay, this all sounds incredibly solid in theory, really well thought out. But what about the proof? What does the data actually say? How does this design stack up against real attacks in practice?
Yeah, good question. The research paper behind CaMeL has some pretty compelling numbers on this. They compared an undefended system, one basically relying on those prompt-level band-aids and hoping for the best.
Okay.
That system achieved about 84% task completion on their test set, which sounds pretty good on the surface.
Yeah, not bad.
But critically, it had a provable security rate of 0%.
Zero, meaning
Meaning, in 0% of the cases, could they mathematically guarantee that the system wouldn't perform an unsafe action based on malicious input? It might work most of the time, but it was fundamentally insecure.
yikes. Okay, so how did CaMeL do?
So the CaMeL system, with all these controls, the dual LLMs, the capabilities, the policies it achieved, a very respectable 77% task completion rate, a slight dip, sure.
Okay, a bit lower, but still pretty high.
But here's the kicker. It also achieved 77% provable security.
Wow. So basically, when it completed the task, you can be sure it did it safely according to the rules.
Exactly. If you connect this to the bigger picture, it shows a really excellent trade-off, especially when you genuinely prioritize safety by design. It pretty definitively proves that careful architectural system design beats just relying on good vibes or hoping the model magically understands your intentions. You're building actual verifiable trust, not just hoping for it.
Okay, that's compelling. So let's pivot then. What does this all mean for you, the listener? If you're out there building AI agents, you want something you can actually ship, something practical, right? Not just theory. Let's move from these high-level concepts to more of a no-nonsense playbook for preventing prompt injection using these ideas.
Absolutely. Let's make it concrete. The first absolutely foundational strategy is to separate control and data. This is that dual LLM pattern we talked about. You need one component, your planner, that writes the plan but never sees untrusted content. And you need a distinct, separate component, your parser, that handles the untrusted content but never gets to call tools.
Right. Make that architectural split.
Yes, that structural decision gives you a really solid anchor for prevention, and it means you're not constantly resorting to awkward, brittle prompt gymnastics trying to tell the model what to ignore.
Okay, strategy 1. Separate control and data. What's next?
Number 2, you need to enforce capabilities at the tool boundaries. As data enters your system, tag it. Attach those passports we talked about, recording where it came from, provenance, and any restrictions on its use.
Tag the data with its history and rules.
Precisely. Then, create really tight, specific policies for your high-risk tools. Things like sending files, making payments, initiating external network calls, HTTP requests, or especially executing code.
And these policies check the tags before allowing the tool to run.
Exactly. And the strong recommendation here is to design these policies to fail closed.
Fail closed, meaning
Meaning, if there's any ambiguity, if a policy check isn't definitively passed, the system doesn't just guess or hope for the best. It stops. It takes the safest possible route, which usually means blocking the action and asking for explicit confirmation from a human user.
okay, like a strict bouncer at a club door. If your ID looks even slightly off, you're not getting in without the manager's okay.
Perfect analogy. This is really the one place where introducing a small amount of potential friction, asking for user confirmation, sometimes pays for itself many, many times over in preventing serious incidents.
Makes sense. What's strategy 3?
Building on that separation, use structured outputs for the parser. Your quarantined LLM, the one handling untrusted data. It should always return its findings as structured data think.json format, defined by clear, minimal schemas.
Not just free-form text or prose.
Definitely not prose. Structured data constrains its power significantly. You can even include something simple, like a Boolean flag in the output, maybe called have enough information for plan. To prevent the parser from trying to sneakily inject suggestions or commands back into the planning process indirectly through unstructured text, keep its output purely informational and structured.
Got it. Keep the parser strictly informational via schemas. Okay, number 4.
This one's simple but surprisingly powerful. Whitelist tools per task. For any given plan the agent is executing, granted access only to the absolute minimum set of tools required for that specific plan to succeed.
So tailor the toolbox for the job at hand.
Exactly. If a user just asks for a simple calendar change, the agent executing that plan should absolutely not have access to tools that can delete files or push code to a repository. Why would it need them?
Right. No reason.
By restricting the available tools just to what's necessary for the current task, you dramatically reduce the potential blast radius if something unexpected does manage to slip through the cracks. The agent literally doesn't have the capability to do unrelated harmful things.
Love that. Principle of least privilege applied to agents. What's 5?
Number 5, require human approval for high-impact actions. This builds on the fail-closed idea. Anything involving sending money, deleting significant data, sharing sensitive information externally, or accessing secrets should automatically trigger a checkpoint requiring a human to explicitly approve it.
Okay. A mandatory human in the loop for the big stuff.
Yes. And the approval prompt itself should be designed carefully. Keep it compact, show the user the context, especially the provenance of the data involved, thanks to those capability tags, and make sure you log the decision who approved it and when. This not only catches mistakes and potential attacks, but also builds crucial trust, especially if you ever need to explain things to auditors.
Good point. Audit trails are key. All right, number 6.
Number 6 is crucial for long-term security, especially as threats evolve. Build observability that survives incidents. You absolutely need to log everything relevant. The plan itself, the schema the parser used, the structured output it generated, the exact inputs passed to every tool, the results that came back.
The work.
And critically, every single policy decision. Log why a policy check passed or failed. You should even try to store those capability tags alongside the data values in your logs or data lake.
So you have the full forensic picture if something goes wrong.
Exactly. If you want lasting prompt injection prevention, you need really good eyes on the system. You need the ability to go back and understand exactly what happened and why, so you can fix the underlying issue.
Makes total sense. And the final strategy, number 7.
Finally, number 7, red team regularly, then fix the controls. You need to proactively test your defenses. Run tests specifically designed to trigger both direct and indirect prompt injection across your most important agent
And
workflows.
don't just use clean test cases.
No way. Use wild content. Scrape real messy web reviews. Use garbled meeting notes. Feed it vendor emails full of typos and weird formatting. You need to simulate the kind of messy, unpredictable input your agent will actually encounter. And here's the most crucial part of this point. When your red team does find issues, and they likely will fix the plan, the schema, or the policy, don't just tweak the wording of your prompt.
Ah, don't just try to out-prompt the attacker. Fix the underlying system control.
Precisely. You're building robust defenses, not playing prompt whack-a-mole.
That's a fantastic playbook. It's really interesting, too, how those specific threats map so clearly to these controls you laid out.
Yeah, you can see the lines, right?
Totally. Like direct prompt injection where the model just ignores instructions that's tackled head-on by isolating the planner and having those rigorous policy checks at the tool boundary.
Mm-hmm.
And indirect prompt injection, which often shows up as just subtly wrong arguments being fed to a tool.
Which is often the sneakier one.
Right. That's where the quarantined parser, spitting out structured data, combined with capability checks on those values, really steps in to prevent harm. That's where you said most real-world issues often hide, kind of flying under the radar.
Exactly. And think about data exfiltration, maybe via a tool call, trying to share sensitive info unintentionally.
Yeah.
That's where tracking capability readers and having explicit policies like, is this data allowed to be public versus only shared with these specific recipients, makes sharing intentional and gated.
And tool misuse, calling an unexpected tool.
That's directly addressed by that pro-task tool whitelist. If the tool isn't even in the agent's permitted toolbox for that specific job, it simply can't be called.
It really drives home the point that prompt injection prevention isn't about finding one magic bullet. It's a portfolio, right? A set of layered defenses.
Absolutely. It's a portfolio approach. The more of these controls you thoughtfully implement, the less exciting and hopefully much less frequent your security incidents are going to be.
Okay, so we have the playbook. What about some key tips for actually implementing this stuff, things that really pay off?
Yeah, a few things come to mind. First, try to keep your plans small and deterministic.
Why small and deterministic?
Shorter, more focused plans are just inherently easier to audit, easier for humans to understand, and frankly, much harder for an attacker to subtly subvert over multiple complex steps.
Makes sense. Simpler is safer.
Often, yes. Second, really think about how you design your parser schemas to minimize the parser's power. If the only valid piece of information you truly need from that untrusted document is, say, an email address and maybe a file name, then define a schema that allows exactly that and nothing more. Avoid broad, free text fields wherever you possibly can.
Right. Constrain the parser's output rigorously.
Yes. This helps ensure the parser doesn't get tempted or tricked into sneaking arbitrary suggestions or commands back into the planning loop. Also, definitely treat your policies as code.
Meaning version control, code reviews.
All of it. Keep them in version control, make sure they're code reviewed just like any other critical piece of your software, and write automated tests for them. Start with the high-value ones like policies for send mail or transfer money or external prequest.
Treat security logic with the seriousness it deserves.
Exactly. And maybe the biggest mindset shift, the final tip, is to constantly think in values, not just strings.
Explain that one more time.
Capabilities, those data passports, need to travel with the data values themselves. So if your agent reads a sensitive document and then generates a summary of it,
Yeah.
that summary shouldn't just be treated as plain, neutral text afterwards. It needs to inherit the same passport, the same capability tags as the original sensitive document it came from.
Ah, okay, so the security context follows the data lineage.
Precisely. Its data provenance, its access rules, they need to follow it wherever that data or data derived from it goes in the system. Getting that mindset right is really central to building truly robust prompt injection prevention.
It's a great set of tips. Now, we also need to be realistic, right? No system, no matter how well designed, stops every single possible failure mode. We have to be honest about the limits here.
Absolutely. Honesty is crucial, and CaMeL's guarantees, as strong as they are specifically focused on preventing unsafe actions taken at the tool boundary.
Okay, so what doesn't it stop?
Yeah. It doesn't really try to stop, for example, purely text-only misinterpretations that never actually result in a tool call.
Like what?
Like, say, the agent reads a nasty, malicious review from a website and then simply prints that malicious text back out to the user in its response. CaMeL doesn't prevent that display of text.
That's okay. But the key is,
The key is it does stop the model from taking that malicious text and using it to, say, send money somewhere or delete files or leak confidential data, because those actions are gated by tools and those tools are protected by the policy's checking capabilities. It stops the harmful actions.
got it. It focuses on preventing concrete harm via tools.
Right. And we should also briefly mention side channels. It's a more advanced topic, but
What are those?
sometimes information can leak out not through the data itself, but through like the system's behavior, maybe timing or how many times something runs.
Okay. Like if a loop runs n times based on a secret number n.
Exactly. An attacker who shouldn't know n might be able to infer it just by observing how long the loop takes to run or counting some side effect.
Tricky.
It is. The CaMeL paper mentions a concept called strict dependency mode that can help mitigate some of this. Basically, it involves treating control flow conditions, like the condition in that loop, as data dependencies themselves, so policies can check if they might leak sensitive info.
Okay. So there are ways to address it, but it's a deeper concern.
Yeah, it's something to be aware of as systems get more complex, but the core CaMeL principles give you the foundation.
This is all incredibly valuable. But it also raises a really important practical question. How do you even begin implementing all of this? It sounds potentially like a lot of work,
It can seem daunting, yeah.
but you've got a strategy, right?
Sure.
Something to help folks move from just talking about this stuff, from slogans, to actually getting concrete prompt injection prevention built, maybe within just a sprint or two.
Absolutely. The key is to start small and focused, then iterate. First step, pick just one of your agents. Choose one that you know touches untrusted data in some way, and identify just one high-risk tool that agent uses. Maybe it's sending email, maybe it's accessing a specific API.
Okay, narrow the scope right down. One agent, one risky tool.
Exactly. Then implement that split planner and parser architecture just for that agent's workflow. Make sure the parser only outputs structured data, like we discussed.
Okay, planner parser split, structured output only. Step 2.
Step 3, really. Add just 2 key policies, leveraging those capability tags we talked about. Maybe start with policies for send mail and external AUT prequest, if those are relevant. And importantly, run these initial policies with confirmation prompts enabled. Get that human checkpoint in place early.
Got it. 2 core policies with human confirmation. And log everything.
And log everything. Tag your values with their provenance and who can read them, and make sure your logging captures the plan, the parser output, the policy decisions, all of it.
Okay, never mind.
Then once that basic structure is in place for that one workflow, red team it immediately.
Test it right away.
Yes. Test it specifically for both direct and indirect prompt injection attempts across maybe 3 realistic task scenarios for that agent. Use that messy, wild data.
And when the red team finds issues,
And remember, when they find issues, and they probably will, you fix the plan, the schema, or the policy, you fix the system controls. You don't just tweak the prompt wording. Resist that urge.
fix the system, not the prompt. Got it.
And then you just repeat the process for your next most critical agent or workflow. You build out this robust defense layer by layer.
That makes it sound much more achievable. Start small, build the core pattern, test, fix the controls, then expand.
Exactly. That sequence quickly builds a strong foundation that you can then extend across your entire stack of agents or AI-powered features.
This has been incredibly insightful. Ultimately, what this whole deep dive really shows us, I think, is that we don't need to just cross our fingers and, beg the model to be good.
Right. Hope is not a strategy here.
We can actually make the system safe by construction, by design. And this CaMeL framework, it really lays out a clear, actionable path to do that.
Yeah, through that intelligent separation of control and data.
Meticulously tracking the data's provenance with those capability passports.
And enforcing clear, strict policies right at the tool boundary, which is where the real risk actually lies. The research community, like the folks behind CaMeL, they've done the hard part in many ways. They've shown, pretty convincingly, that this kind of careful architectural design demonstrably beats relying on just good vibes or clever prompts or, frankly, just hope.
Right. The proof of concept is there.
It is. So now it's really on all of us, the people building these systems, to actually implement these more resilient designs.
So as you, our listener, wrap up listening to this deep dive, maybe consider this final thought. What's just one workflow, one process in your domain that touches untrusted content? Where could you apply this split planner design, maybe attach some capability tags, and implement just 2 high-risk policies, perhaps with confirmation prompts starting today or this week?
Yeah, pick that one spot.
And then try to measure it. How often do you actually block potentially unsafe actions? thanks to those new controls. And please share your stories, your findings with the broader community.
We need those real-world examples.
We really do. Because the community needs more real stories about prompt injection prevention that actually works in practice, not just more theoretical discussions or lists of clever prompt hacks that might break tomorrow.
Well said.
You can start building that safer, more reliable future for AI agents today.